Welcome to Math 331, problem solving. This is lecture 31, and we're going to continue doing some Putnam problems. And so, yeah, it's having issues displaying things today. All right, so we were looking at a couple of problems from last time. So we were looking at, in particular, an A1 or B1 proposed problem about looking at sums of factorials. So let's let Fn be 1 factorial plus 2 factorial all the way up to n factorial. Try to find polynomials Pn and Qn such that Fn plus 2 equals Pn Fn plus 1 plus Qn Fn for all n greater than or equal to 1. And if things were working better, I might be able to toggle back to some of the stuff we were doing. But it does not seem like it's letting me do that today. And so in the last lecture, we talked about several different ways to attack this problem, in particular gathering data and trying to get a sense. And one possibility is if we believe P and Q are, exist, which is not an unreasonable thing to do since the problem says find polynomials P and Q, then if they have sufficiently low degrees, there's not too many things to try. And it turns out that the solution involves P and Q being linear with leading terms 1 and minus 1. So you really can get them without too much trouble. Let's see if I can move to the next slide and just go through. We talked about several different approaches last time. So one more time. All right. I think it was Fn was 1 factorial plus ... plus n factorial. We wanted Fn plus 2 to be Pn Fn plus 1 plus Qn Fn, right? And the idea that we had at the end of the last class was to write Fn plus 1 as n plus 1 factorial plus Fn, and Fn plus 2 as n plus 2 factorial plus n plus 1 factorial plus Fn. And when we substitute, that will give us n plus 2 factorial plus n plus 1 factorial plus Fn from the left-hand side is equal to Pn times Fn plus 1. So it'll be n plus 1 factorial plus Fn plus Qn times Fn, right? So if we just put all the Fn's on one side, we would have n plus 2 factorial plus n plus 1 factorial minus Pn of times n plus 1 factorial equals Pn plus Qn minus 1 times Fn. Did I make a mistake or is the algebra correct? So then the question is just, can we find polynomials P and Q such that this is true? And this is written, so the hope is that choose to be 0, and then choose Pn to be 0. And what's nice is Qn doesn't occur in the first part. So if we can find a Pn that works, then the hope is we then have the freedom to choose Qn to make the second work. And once we look at the problem like this, it's going to fall immediately. So clearly there will always be a Pn that works. The only question is whether or not it will be a polynomial, right? If it's not a polynomial, then we're in trouble. But if it's a polynomial, then hopefully we can solve for the other one. And in fact, that won't be that bad because if there is such a Pn, what would Qn be? So if there exists a Pn such that the left-hand side is 0, what should we take Qn to be?
1.
So if we can find a Pn such that the left-hand side is 0, what should Qn be? What do we want the coefficient of Fn to be?
0.
0. So what should Qn be if we want that coefficient to be 0? sorry?
Pn plus 1.
Not Pn plus 1.
Negative.
Negative Pn plus 1. So it's negative Pn plus 1. And so if Pn is a polynomial, Qn will be a polynomial. So if Pn is a polynomial, so is Qn. So this is looking real good. So the only question is there a polynomial that works? Well, on the left-hand side is the same as n plus 2 plus 1 times n plus 1 factorial minus Pn n plus 1 factorial. So this is just n plus 3 minus Pn times n plus 1 factorial. So Pn is just going to be n plus 3. And thus that implies Qn is going to be negative Pn plus 1. So it's going to be negative n minus 2, I think. Assuming we haven't done any algebra mistakes. So what's nice about that is if we had gambled and assumed that P and Q were both linear, we would have actually only had 4 coefficients to look at. We could have found it by looking at the first 4 pieces of data. So if hey, it's letting me toggle back now. Okay. So this data table would have been enough to figure out what those coefficients were. And then we could have checked to see that the recurrence would keep being satisfied. So anyways, I thought this was a particularly fun problem. There's a lot of ways to look at it before you get to the answer. And then once you find the right way, like a good Putnam problem, it's really fast to get to the solution. And here, I think the best way is to write Fn plus 1 as n plus 1 factorial plus Fn, is to just use the fact that we can define this function in terms of previous values. And that simplifies a lot of the arguments. The next problem I want to look at was this proposed problem on triangles. So let me see if I can copy it. And let me paste it down here. Okay. It is one of those days. All right, we'll paste it twice. All right, I'll try to fix the image later. So here's the problem. Let T be a triangle, and R and S are inscribed in T as follows. Find the maximum value or show no maximum value exists of the area of the R rectangle plus the area of the S rectangle divided by the area of the whole triangle. So what's your first thought when you look at a problem like this? So one is, how can you know maximum exists? So the first is, does a max exist? What's your next thought? Yes. As a proportion of the area. Yes. What should be your thought on any Putnam problem? Gather data, right? So maybe certain triangles are easier to analyze than others. If you had to choose a triangle, which triangle would you choose? What should you choose for the initial triangle T? Equilateral. Equilateral. So candidates. Equilateral. It is hard to argue against equilateral, right? This is the triangle with the most symmetries. What's another natural candidate? Okay, which right triangle? Okay, be more specific though. Isosceles right triangle, right? And then after that, just a generic right triangle. But you brought up an excellent point. Does it matter where the angles are? So for example, what about an obtuse triangle? And say, let's say I give you a triangle like this. Is that going to be a little bit different in terms of how things look? Because if I gave you a triangle like this, and I'm now trying to fill things, I can't go all the way like that. So are things going to be a little bit harder if I give you a triangle like this? This is a huge point to think about, that frequently something is drawn in such a way to force you to look at things in a particular perspective. And that may not be all possible cases. So I just was looking at a proof of Fermat's last theorem. Oh, so not Fermat's last theorem, something else, sorry. Where the author did not realize that he has to break it up into two cases. Something is zero, something is not zero. Because technically he might have divided by zero. It was trivial to handle that case, but you had to be careful about this. When I'm looking at this, I'm making the assumption from how the picture is drawn that I'm going to have two vertices hitting the two sides of the triangle, and they're going to be the vertices at the same level of each rectangle. So here it's going to be these two vertices hit, and then these two ones miss, and then these two hit, and then these two ones miss. Whereas over here, the two ones that hit are now opposite of each other, and these are the two that miss. And over here, I guess these ones hit, but they're not hitting the sides, they're hitting the bottom. And so here, these would be hitting the sides, and these ones would not. So does it make a difference if I have an obtuse angle down below? Okay. So my first thought is to try to get a sense of which triangles can we study. And so I like the idea of looking at isosceles. I like the idea of looking at right triangles. I like the idea of looking at isosceles right triangles, trying to build up some intuition. And for each of these problems, see what we can do, and then consider what happens as we vary the triangle. So my first thought is it would be wonderful if I could make the following assumption. From here, I could reduce to just considering maybe a right triangle. And again, I have no idea if this is going to work, but my first thought is draw the perpendicular like this. So if I have my sides, I've got my first one like this. I've got my second one like this. It would be interesting if the relative area on the right-hand side to the area of the triangle on the right-hand side is the same as the relative area on the left-hand side to the area of the triangle on the left-hand side. Because if so, then I can reduce it to two identical problems. This is similar to, we did the Farmer-Brown problem, where Farmer-Brown wanted to find the rectangle that could contain the most cows. And then we had not just Farmer Brown, but we had the Farmer Bob, where he was on the water. And the way you solved that was you had Aquaman building the mirror image below. And if you do that, it's enough to just consider what's going on in the top, and you reflect it for the bottom. So if we could show that you have a certain optimal on one side, and it's the same as percentage-wise as the other side, then all of a sudden the problem is a lot easier. We can assume our triangle is right, so long as the vertex above is somewhere between the vertical lines coming up from the side on the x-axis. If the point is beyond that, then we might have some trouble and we might have to play some games. But again, I'm trying to get a sense of what can I reduce it to prove the result. the next question is, if I can prove it for a right triangle with a given side. So let's say I have an optimal So let's say I have an optimal configuration. Imagine I now stretch. And my question is, if I then stretch these, would they stretch proportionally? And would it be at the same heights down for the optimal? Does that make sense? Then I'm basically saying, if I figure out what the optimal distance to move down from the top vertex is for my initial right triangle, if I then swing out the base further, if that's still going to be the same optimal, then I might as well assume I have an isosceles right triangle to begin with. So again, this is just my initial thought when I see a problem like this, trying to get a sense of what to do. We can try to prove results like this if you want. We can try to analyze an isosceles right triangle or a equilateral triangle. There's lots of ways to go. And again, you have 3 hours on the Putnam. Most of the problems you're going to have no idea how to do, even if you have 10 hours. So it's not a bad strategy to just spend a couple of minutes, stay calm, and just say, and take a deep breath, going to have a drink, and I'm going to just spend 10 minutes gathering data. And then I'll start to decide which way I want to go. But it's not a bad life lesson to just spend some time and get a lay of the land before you commit your resources. Anybody ever play Stratego? The old game where you have the pieces facing you with their numbers. And you have to try to figure out where the enemy has their high-ranking pieces. And so you often send out scouts. And we salute them for their service to the cause as they die. But their goal is to get a sense of what's out there so we can then deploy our forces effectively. And so take a couple of minutes and try to figure out. We have a couple of options here. Do you want to try looking at a specific triangle? Do you want to try to prove that if I swing out the side, as long as I keep it as a right triangle, the relative, how far I have to go down is not going to change? Which would you rather do?
We stick to a given triangle, we might be able to construct a differential system that we can solve to find an expression that gives us where the height should be.
Okay, so it might be independent of the only thing about that is that might mean that the equations for the triangle will be a little bit more involved. If it's an isosceles right triangle, things might be a little simpler. So that's the trade-off. We can absolutely do it that way. It all comes down to trying to use the phrase, without loss of generality, we can assume we have an isosceles right triangle. If we can do something like that, that's terrific. If you want to just try to do things in general, we can do that. And again, either way is fine. This is your chance to choose which way the class goes. It's a choose your own adventure. Does anybody at least read those books? All right. So which would you like to do? Do you want to do general triangle, or do you want to try to prove we can assume isosceles right? I'm sorry? Okay, so we're gonna just try that first and see if we can do that simply. So let's try an isosceles right triangle. And of course, what's the length of the side? It's 1 unit, right? If it's going to be isosceles right, it might as well at least be a 1 by 1. And so we have our 2 points where we come down. If you had to guess, anybody brave enough to guess how far you might go down? One-third. I think that's an absolutely stellar guess. Think about it. You want, if we move this point up a little bit, by moving that up, we increase the height, but we decrease the base. So depending on where we are, that might actually be a good thing to do. But of course, as we do that, that then has impact for the next triangle. I mean, for the next rectangle. It's going to decrease it by a little bit. And so, what's really happening is it's this area here versus this area here. And just, when is that worthwhile? Okay, so we have to think about the notation we want to use. And so there's lots of different ways we can do this. We could say we go down x, we go down y, and x and y are two numbers between 0 and 1. So we could do, 0 less than equal to x, less than equal to y, less than equal to 1. We could, I'll just use different numbers. We could do p plus q, 0 less than equal to p, q, p plus q, less than equal to 1. Where q is, yes?
I'm wondering if the optimization that we're looking for is analogous to minimizing the area of that middle triangle cutout with, compared to the added area of the two rectangles.
So you want to say, is it equivalent to minimizing this?
Yeah, compared to the L shape.
But what about the stuff up here as well?
Well, I'm just thinking if we were to take that top rectangle and like
Right.
Triangle in the middle, seems like that would be something.
But like, okay, but if the top rectangle is made super thin, then the middle rectangle.
We can make the middle rectangle
super small, but
right.
still, that's not optimal.
We can still we can make the middle rectangle very, very small by just moving these 2 points close to each other. But that will then, of course, make the area of those other two rectangles smaller. So there might be a way to do it like that. But I think that's going to be more work. I want to just get a sense of how hard would it be to just calculate what the area will be in this case. So to me, these seem to be the two natural coordinate systems to use. I've got x less than equal to y less than equal to 1, and I've got p, q, and p plus q less than equal to 1. Does anybody have a preference of which way we do things? PQ? You can do it PQ. Now, because this is isosceles right, without loss of generality, what can we assume about P and Q? Which one is larger? Can we choose one of them to be larger if we want?
Yeah, I think so.
Yeah, because it's completely symmetric. That's the nice thing about isosceles right. Because of the symmetry, I can either make P larger or Q larger. So this triangle here is going to be P by Q, right? Because it's isosceles right, if this is P, this is P. And this side here is going to be P plus Q, and this is going to be 1 minus Q, I think. Yes?
Why is that 1 minus Q?
Was it 1 minus P plus Q? Oh no, sorry, it's 1 minus P plus Q. It's 1 minus P plus Q, sorry. So that's using the PQ coordinates. If we use the XY coordinates, and again, take a moment to just see which is best. It's okay if you can't instinctively look at the problem and know which is best. If I use this is X and this is Y, then this would be X over here. This would be Y minus X, right? And then this would be Y minus X, and this would be 1 minus X. So here, we would get the area as a function of P and Q would be, I think, PQ plus P plus Q times 1 minus P plus Q. And here we would get area as a function of x and y would be x times y minus x plus y minus x times 1 minus x. Which seems cleaner? I think the second one seems cleaner with the x and the y. But again, I don't think it was immediately apparent which one was going to be easier. And I think these are the two natural ways to look at it. Is basically I'm walking down and I walk down p%. And then I have to walk some additional amount. So what's nice is, let's just double check. Are we confident that we have a of xy correct? X times y minus x. Then because it's a right triangle, that would be y minus x. Oh no, it's not 1 minus x, it's 1 minus y at the end, isn't it? That's 1 minus y, correct? It's 1 minus y for the height, correct? Okay, so we get, we could simplify things a little bit. There's a y minus x times everything. We could write it as a of xy equals x plus 1 minus y times y minus x. And now we have to figure out what's the best choice of x and y. Do you want to make x larger or y larger? Do you agree that we can choose either x or y to be larger without loss of generality?
Yeah.
Okay, so without loss of generality, either x is greater than or equal to y, or y is greater than or equal to x. When you look at this, this is a function of two variables. We need to find the value of x and y that maximize this. And that will give the answer for a specific triangle. It seems quite reasonable that if I fix the triangle, there should be an optimal. And this is where you use a result from real analysis. If you have a continuous function on a closed bounded set, on a compact set, then it attains its max and its minimum. How would you try to find what value of x and y maximize this? What would you use? Okay, how? So how would you do this? So what derivative would you take? How would you do it? What class do we have to remember now? Multivariable calculus. So how would you maximize or minimize a function of two variables? Fortunately, none of you took multivariable calculus with me, so I don't have to question mine. So given the lack of enthusiasm for trying to do this as a problem in multivariable calculus, let's do a rewind. What did you know before multivariable calculus? Single variable calculus. So let's do this as two single variable calculus problems rather than one multivariable calculus problem. Could it take longer? Sure. And because this is
How
being...
do you do this in multi?
Well, so in multivariable calculus, you take the gradient and set the gradient equal to 0. And that gives you interior maximum minima. But then you have to worry about the boundary.
Yeah.
And so, here, what are the boundary values of x and y? So let's do it as two calculus problems. Calculus 1 problems. And let's assume y is less than or equal to x. Okay? So here's the function. I cannot move it over close enough, right? So we will assume 0 less than equal to y less than equal to x less than equal to 1. We want to maximize the following. Well, let's fix x and find the best y for that x. And then we vary x, right? So we first go down a certain amount and then see, once we've gone there, what's the best we can do? Is that reasonable? That seems reasonable, right? We have freedom in terms of where we go for the next one. What would be the worst choice for y? Zero, because then we then get absolutely nothing, right? And what's the second worst choice? 1 minus x. Oh, no, sorry, it would be 1, it would be 1, yes, you're correct, I'm wrong. It would be 1, going all the way down, going all the way down. So we already know that the extremes are bad. So we know y can't be more than x by symmetry, but we know the extremes are bad. Extremes are bad. Area is 0 if y equals 0. I'm sorry, if y equals x, the way we're doing the notation, or y equals 1. So if we're looking at it like this, we might not even want to use that y is less than equal to x, yes?
Okay, why are we using x greater than equal to y? Cheat with y minus x.
Sure. And in fact, I think what we're just saying here is we actually don't even need to use this. So, right. Although, let's see, we were saying if y is less than x, yeah, this would become, yes. Okay, so assume 0 less than equal to x, y less than equal to 1. So there was no need to try to put in something like that. But then did we make a mistake in how we formulated things? Oh, so the way I drew the picture with y greater than equal to x. Sorry, it would have to be that the way the picture is drawn, because it's further down, so y minus x has to be positive. So it would have to be y goes from x to 1. So without loss of generality, we can have x less than equal to y less than equal to 1, you know, check extreme cases, get 0 added area. So if y is equal to x or if y equals 1, there's no area from that second rectangle. So that's clearly a bad choice. So now we just want to figure out what's the best value of y between x and 1 that we could choose. So how would you find the best value of y from that equation? What would you do? Good. And so how should we take the derivative of a with respect to y? Absolutely. So anybody know who my favorite New England transcendentalist writer is? Anybody know any New England transcendentalist writers? There's not that many.
What era?
Like mid-1800s? Nope. Thoreau. Anybody know his big piece of advice from Walden?
Oh, Ralph Waldo.
No, from Walden Pond, not Ralph Waldo Emerson, from Walden Pond. So I think Thoreau is the patron saint of mathematics. So his advice was simplify, simplify. Now, of course, you could simplify to simplify, but I think the additional simplify really drives home the point. Think about what truly matters. And before you spend any time doing calculations, stop for a moment and think, is this the calculation I want to do? Or could I simplify things a little bit first and then have a much easier calculation? With a little bit of algebra, we see a of x, y is the same as x plus 1 times negative x minus y squared plus xy. And the reason I'm not multiplying it all out is because I'm about to take the partial with respect to y. I don't care about anything that doesn't depend on y. So I don't have to bother multiplying x plus 1 times negative x. I could do that if I had to. I don't really care to. I don't want to use the product rule to take the partial derivative. Much better to expand it out. And so we get dA dy is equal to whatever the first one is. You can say, okay, so we get negative 2y plus x. So dA dy equals 0 to get the critical point means negative 2y plus x equals 0, which means y equals x halves. And so now we get a of x. I'll do it this way. I'll call a new function area of x is going to be a of x, and then y is x halves. And that's going to be x plus 1 minus x halves. So that's x halves plus 1, right? And then y minus x is going to be wait a minute. Did we make a mistake here?
Is that 1 minus x?
So the first one is x plus 1 minus x halves. So for the second one, is it x halves minus x, which is going to be negative x halves? Something is wrong here, because y is supposed to be between x and 1.
Get to x plus 1 times y.
Now let me check and see if we made an algebra mistake somewhere. We had x times y minus x plus y minus x times 1 minus y. So we definitely have, okay, so the first triangle is x by y minus x, and y is greater than or equal to x. That's fine. And then the next is going to be y minus x, which is a positive number. And then its height is going to be 1 minus y, which is a positive number. Both have a y minus x we can pull out. So we have x plus 1 minus y. So x plus 1 minus y, y minus x.
Multiplication of first term also. So it should be x plus 1 times y. Now the slide will simplify
Right here.
on the next slide.
Okay.
So I think this should be x plus 1 times y plus x plus.
We've got the x plus 1 times y. There we go. Thank you. Yes. So we have x plus 1 times y. So we've got that over here. So we also have a x plus 1 times y. Good. And so when we take the derivative, okay. So then good. So now when we take the derivative, we get negative 2y plus x plus 1. So dA dy equals 0 implies negative 2y plus 2x plus 1 equals 0, or y equals 2x plus 1 over 2, which is x plus 1/2. All right, that's at least larger than x.
So it's definitely particular to this triangle.
Right now, the 1/2 is moving down significantly from x. So let's double check. X plus y, so x plus 1 times negative, okay, so you have a negative y squared. We have a plus xy. And we have an x plus 1 times y. We have an x plus 1, we have an x, we have a minus 2y. Okay, that seems reasonable. Okay, so then we would have area would be a of x, x plus 1/2. And so going into our area function, we would have x plus 1 minus x plus 1/2. So I think it would just be 1/2 for the first factor. And 1/2 for the second factor. So if that's the case, it's basically saying whatever x is, we can find a value of y to get the same area. That there's no benefit from optimizing for x. We may have made an algebra mistake. I think we've caught all the algebra mistakes. To just be safe, here was the other formulation. And so let's just double check with the derivative one more time. dA dy. So this is going to be xy minus x squared. Let's just expand everything out. Plus y minus y squared minus x plus xy. So dA dy would be x plus 1 minus 2y plus x. And that's the same as what we got before. So it looks like dA dy equals 0 implies 2y equals 2x plus 1, or y is equal to x plus 1/2. And so then the area at x and x plus 1/2 is going to be x times 1/2 plus y minus x is 1/2. And then 1 minus y becomes 1 minus x plus 1/2 becomes 1/2 minus x. And so the x halves and the negative x halves cancel and you get 1/4. So what this is saying is for an isosceles right triangle, if you optimize, you're always going to get 1/4 for the area. And it doesn't matter what you choose over here. Go down half a unit. And that will give you, 1/4, and that's the best you can do. So I'll admit, I'm a little surprised by this. I would have thought that it would matter a little bit about what goes on. Oops.
I feel like my intuition is 1/2, but shouldn't it be a third?
I would have thought a third. And that's why I'm wondering if we have a mistake somewhere. Now, if you take the limit, not sure why this is going on here.
So if we had first taken the partial with respect to, we expect to get the same value for area.
We should. We can do that right now as a quick check. The other thing is, if you consider the extreme case of taking x to 0, as x goes to 0, putting things in at 1/2 is giving you the largest thing over here. And then as you start gaining some red, you're losing some in the blue. I would have thought it would have been 1/3, 1/3. And that's why I'm wondering if we've made an algebra mistake somewhere. I mean, again, right now I'm not doing surgery on someone, so if we make an algebra mistake, no one dies. I care more about the thought process that we can do this as a two-stage calculus problem. So if you forget your multivariable calculus, we can do calc 1 twice. You fix x, find the value of y that optimizes for that fixed x, and then plug that in, and now we have a function of just x and optimize that. So even if we've made an algebra mistake, we've at least got a good thought process to this. And so for Wednesday's class, we can go through and then look and see, have we made an algebra mistake? Or is it really just 1/4 independent of where you do it? That whatever you gain in the red, you've lost in the blue, and it's equal. The next thing, we've got 1 minute left today, is what would happen, let's say we have some optimal configuration. What happens if we extend? So now, if we extend, let's think about how much we rescale things by. So if this was 1, let's rescale it to be R. So if this was U and this was V, how much is U going to be rescaled as we swing things out? If we go down by the same height, so you would need to figure out how all that is done. And so I'll leave you to think about this. It might be from this point that, what? It might be easier to just say, let's assume our initial triangle is here's 0, 0. Here is, maybe R comma 0, and here is 0 comma 1. And just look at my right triangle like that, and then give myself this extra parameter R over here, and instead of doing the isosceles right triangle, do all of these triangles. And then maybe we wouldn't get 1/4 every single time. Maybe the answer would depend. So we can then go through and see how much harder would the algebra be if we had that as our triangle. Yes?
Won't this be different because when the triangle, it's not going to be isosceles right triangle?
Right, no, so we would have to write down the equations, and there would be a little bit more work to figure out the areas of the rectangle. The area of the rectangle is very easy to calculate because it was isosceles, right? But it's not terrible here. We can, write down the equation of, what that line is and figuring out what the corresponding sides are. It's just, if we could assume without loss of generality that, things scaled nicely, I'd much rather use an isosceles right triangle. All right, so this is a good place to stop. And then since now we've now discussed it in class, now I can go home and think about the problem and then report back. But I didn't want to think about it before the lecture.